This is mainly a notebook presentation for the classification task learning, and I have already posted the notebook on my GitHub, and here is the link, and you will find also the link in the description box of the video. Just like the way we have demonstrated the regression modeling through few examples, we'll be doing the same for the classification modeling. And as usual, I will be sharing this notebook, but the first notebook that we'll be presenting today is a classification problem on breast cancer data. That we'll be learning few different models, logistic regression, random forest, support vector classification, and boosting and naive Bayes. So here I'm loading corresponding scikit-learn modules. So you can see that logistic regression, and then random forest classifier, grading boosting classifier, then Gaussian naive Bayes. And here we have the support vector classifier. So let's load the modules, and here I have put the link. So feel free to go to that link and read about the details of the dataset. Here I'm loading the dataset, and we can see that the dataset has 569 entries and 30 columns. And if we look at the first few records, we see that there are features something like mean radius, mean texture. So I think they are talking about the cancer cell related information, and these are statistical information. So feel free to go over all the features, more learn about the dataset. And here, because this dataset again is curated by the scikit-learn community, so there is another method you can use to load the dataset is load breast cancer, and then if you parameterize return _x _y equal to true, then you will get the x and y matrix. So here I'm just looking at that how many unique values have in the y column. That is the level array, and you can clearly see that it is a binary classification problem with two levels, 0 and 1. Okay. Now here I'm checking one thing that you should try in any of your model development activities, that when I have the data matrix, if I just print the minimum and maximum value, then I will have some idea about whether we need to actually normalize data or not. So if you see that you have minimum value 0, but there are some values that are actually more than 1, So if I go back to the data frame, we can see that some of the values are actually maybe within range 0 and 1, but some of the values are not scaled, So although here we are loading data from the scikit-learn pre-processed data, but not necessarily all the data they have provided as normalized data. So it is on us, because we know that normalization is a standard procedure. Some of the models actually rely on normalized data, otherwise it won't work, So if you recall, we are using the same normalizer or scalar, what you call mean max scalar, that we used for some of our experiments for the regression task. So I'm doing the same for this particular data set, and now as I scale my data, if I run the same, you will see that the values are actually 0 and within 1. So as our data is scaled, I'm just assigning back to x, because the x matrix we have and we'll be using quite frequently. So I don't want to change my code a lot, so I'm just assigning these values. Here I'm testing for a 50-50 train test split, just the way we have tested our regression models earlier. Okay. So here I'm splitting 50-50 for 50% training and 50% test. For classification, we'll be using logistic regression, not linear regression. Okay, linear regression is for the regression task. Okay, and I am naming my model as CLF. So you have your model being instantiated, and you are fitting your model by passing your training data and training levels. As we did for the regression task. Okay, now we have our model trained. And now I am doing the prediction with my test data features, and the metrics that we are actually looking at is the accuracy. So if we recall, for our regression problems, we used the mean squared error as our error metric. But here, one intuitive metric is actually accuracy. Accuracy meaning that how many of the predictions are actually right, the ratio of the predictions are right. For the classification task, we have to use the evaluation matrix quite sensibly. It's not necessary that we have to always use the accuracy metric. It's not proper to use accuracy metric for all problems. We'll learn about that. Okay. So as I mentioned, here we are talking about how many data points were misclassified and how many were actually properly classified. And again, here we are talking about a binary classification test. So one very cool way to show your data that how the model is performing is through what we call a confusion matrix. Okay. So here we are passing our actual test levels and then predicted test levels. Let's run that. And so here you will have an confusion matrix instance, and then we are just plotting that that confusion matrix. So here the y-axis is the actual levels. So you see like 0 and 1, and then the x-axis are the predicted levels. So you can see that out of 70 negative levels, 66 were rightly identified by the classifier. For the class with level 1, I think most of them were properly identified. So out of 215, 214 were actually rightly identified by the model. So the model is actually doing pretty good, about 98% accuracy. So again, the confusion matrix is a very intuitive or efficient way to how the model is actually performing, and we will use the confusion matrix to actually explain some other metrics. So just keep it in mind. The last time we were doing a 50-50 train test split, but here we are doing a random splitting. More specifically, here we are talking about 80% training and 20% test splitting. But the process is quite the same as we did for our regression activities. And again, I'm using the same wrapper class that we used for our regression modeling, but I'm just renaming it as my classification model. One thing is that I have to change the evaluation metrics, because in the regression we use mean square error, but here we are using the accuracy as our metric. Okay. So let's run that as we have done for the regression tasks. I am instantiating a logistic regression model, and I'm using my 80% test train split to see like how the model is actually working. Okay. So you see that for the 50-50 test train split, the test error was about 98%, but here the accuracy actually dropped a little bit, but the training accuracy is quite close to what we have seen for the other setup. If you want to see the cross validation scores, the cross validation scores looks like this. So the mean of the cross validation accuracy is around 97%, so it's close to what we have seen for the other two setups that we have run earlier. But here the standard deviation is 0.008. Just keep this in mind, because we will be comparing these numbers with some other models. So here we are doing the same for the random forest classifier, and if you notice that the random forest classifier was actually able to classify all the training instances, so the accuracy is just 100% or perfect one, but the test accuracy is not a lot better than the logistic regression model, but it's still better, almost 97%. And if we run the cross validation metric, we can see the average is around 96, so it's less than what we have seen for the logistic regression. And more importantly, you see that the standard deviation is a lot higher than what we have seen for the logistic regression model. So in both cases, the random forest model is not doing as good as the logistic regression model. But again, here we are not coming to the final conclusion, because one of the items that we discussed for the regression task as well, because here we are talking about only 500 plus data instances, and that's why the random forest model is actually overfitting, and we have ways to actually improve the models that we'll be learning in the coming days. Okay. So I'm going to not take a lot more time because the others are actually you do the same and you check for other models. So here the support vector regression is doing I think pretty good. Almost the accuracy is 98%, even the cross validation accuracy, and the standard deviation is kind of also good. You can do the same for the boosting and check how the results look like. One thing is will be interesting. Here we have a new class of model, what we call naive Bayes model. At some point we'll be explaining that what are the underlying mechanics of the naive Bayes model as well as other models, but we didn't have naive Bayes regression. Just keep it in mind because this is purely a classification model. Okay, but the results are not as good as other models if you carefully observe the numbers here. Okay, so I'll be sharing this notebook, but in summary we have actually exercised few different models for a specific problem, breast cancer prediction, that is a binary classification test. And we have seen most of the processes are almost the same as we have done in our regression model learning, but I was just giving some additional concepts. For example, here we have different evaluation metric, and we also talked about confusion metrics. Okay, so feel free to run this notebook and try to understand what we have just explained, but feel free to reach out to me if you have any questions. Okay, thank you so much.